Hi everyone, congratulations. This will be the final theoretical lecture of MATC58, so if you've made it this far, you've nearly made it to the end. The remainder of the class after today's lecture will be primarily on biological examples, applying some of the mathematical techniques we've learned. But we haven't really, getting back to the topic at hand, we haven't really talked about global stability in differential equations, and it turns out that that's kind of hard to assess sometimes. Sometimes you can figure things out from a phase portrait, but other times that's not sufficient. And so in today's lecture, we're going to talk about global stability and something called Leoponov functions. So first, let's recall some of the things we had back when we were dealing with difference equations. So in section 2.7.2, we defined something called Leoponov exponents for difference equations. So let me just remind you what those were. Exponents for difference equations. Let's say a specific first order difference equation xt plus 1 is equal to some function f of xt, and that was defined by lambda of x naught, where x naught is your starting point, is equal to the limit as t goes to infinity of 1 over t times the average of the first derivatives along the trajectory, along the discrete trajectory that we had from our difference equation. Okay, and what we had there was that if the Leoponov exponent was greater than 0, then there is sensitive dependence. So this is related to chaotic dynamics, but there is sensitive dependence on the initial condition on starting point x naught, which is to say that if you start if there's sensitive dependence, even if you start close to x naught, if you don't start exactly on it, then over some amount of time, the two trajectories will diverge. One of the important things about Leoponov exponents is that lambda of x naught is equal to lambda of x1 is equal to lambda of x2, and so on. And this is, of course, because you're taking a limit as time goes to infinity, and so some finite number of points early on doesn't change your Leoponov exponent. So this is because we cared about asymptotic behavior. So can we do something similar with differential equations? So can we sort of chain together a trajectory and say like, oh, well, if the trajectory later on goes to 0, or goes to some equilibrium, then some trajectory that goes to it also goes to that equilibrium? And the answer is yes. And we already saw this a little bit with our diagrams on the phase line. So which in 1D, you can have things like, let's say we have our x-axis. So we're again working with autonomous equations because otherwise things get really confusing. And if we had some equilibrium here, and we had, say, this is x dot of t. Well, let's say this was, yeah. So this is x dot of t. So it determines which direction you're going. And so that means that over here you're going inward, and over here you're going, well, in both directions you're going inward. Because of the first derivative, and so we can get global stability if everything points towards your equilibrium, and nothing like stops. Okay, so that's in 1D though. So now what about in 2D? In 2D it gets complicated because you have all these different directions you can point. So for example, things get complicated because you might have some trajectory. So let's say this is some trajectory x of t is equal to the low x of t, the low y of t. And given this trajectory, you might have some point here that goes in this direction. So let's say this is x of t naught, and this is x dot of t naught, and so on. So you might have some other point here, which is x of t1, and that points in this direction, x dot of t1, and so on. So it gets a bit harder because the derivatives don't just point in a single left or right. They can point in any direction in 2D, which makes it a little bit harder. But now, so we need to find some way of generalizing this idea of successive constraining to the 2D. So now let's suppose that we have a very specific case. So suppose that we have some equilibrium. And if you recall, one of the tools we used when we were talking about Poincaré-Bendixson was we would constrain our trajectories to be that start in some area to remain in that area. So these sorts of enclosing regions. So suppose that you could, let me actually change my paper style just to make drawing a little bit easier. So suppose that we have some point here, and we can draw a circle around it. And suppose that we can draw concentric circles around it. And suppose that we knew that for all these concentric circles, things point inward. Well, if things always point inward, then you know that if you are ever in one circle, then you're trapped within that circle. And if you get into the next circle, then you're also trapped in that circle. And so if you have some continuous family of circles and everything always points inward, well, then you can say something about global stability for everything in any one of these bigger circles. So the idea here is construct concentric circles around an equilibrium. And equilibrium for every radius r. And of course, you need every radius, because if you skip a radius, then maybe it might stay in that area. That might be a limit cycle instead of everything pointing inward to get global stability. And so if trajectories, if the vector field, let's say, vector field always points inward, then anything in that region will eventually go to the equilibrium. And we can think of these concentric circles as sort of steps that you're taking. So you're getting closer and closer. And this sort of is the same as if you're up in this 1D case, and where you're getting closer and closer from both sides. Here you're just saying that, well, your overall distance from the equilibrium is constantly getting closer and closer, and therefore eventually you'll reach it as time goes to infinity. As the steps the solution takes. Okay, and just to be clear, this doesn't just work with circles. This also works if you have boxes. So if you have boxes and everything points inward. And so we use very similar techniques for to trap trajectories in a particular region by just having one box. But if you have an entire family of boxes, well, then you can slowly push all the trajectories inward. Let's have a couple more arrows. And importantly, this also works for other shapes. So long as you have a continuous family of shapes for other shapes. So for example, maybe you have something that you have some shape here, and that shape is slightly different for the next range. And so long as you have some continuous morphism of the shapes, it also works. And this suggests that in order to prove global stability, all we have to do is construct a family of shapes, a family of enclosing shapes such that all the vector field directions point inward at all times. Now, this is not necessarily that easy, since often the shapes that we need to construct are super weird. But this is the general intuition behind what's called the method of Leoponov. So this is the method of Leoponov for differential equations as opposed to difference equations. And so let's describe it first, and then we'll give you a theorem. So let me change my paper style again. This is a bit too big. Okay, yeah. So the method of Liapunov. So again, we're going to start by considering a 2D autonomous system. The method does work for higher dimensions, but it gets even more complicated to work with. So we're not going to consider that in this course. So let's consider a 2D autonomous system. Let's say dx dt is equal to f of xy, and dy dt is equal to some function g of xy. And we're going to assume, without loss of generality, that the origin is our equilibrium of interest. So if it's not, you can just translate the entire system so that to move whatever equilibrium you want to be at the origin. It really doesn't matter, but it makes our analysis a little bit easier, our definitions a little bit easier. So let's go ahead and this is definition 5.10. What we're going to have to do is we're going to define something called a positive definite function. Some of you may already be familiar with this concept from linear algebra or optimization. This is basically, this is closely related to the definitions from those areas. So if let's have some region, an open subset of R2 be opened. And let's say that the origin point, 0, 0, is in U. Okay, so it's some open neighborhood of of the origin, or in general of the equilibrium. So then a real valued function, v from U to R, with continuous partial derivatives. So this is the C1 function. Is positive definite on U if there are two conditions. So v of 0, 0 is equal to 0, and v of xy is greater than 0 for all xy in U with such that except 0, 0, obviously. Okay, so that's easy enough, right? So it has to be 0 at the equilibrium and non-zero and positive everywhere else, and then let's call it positive definite. Let's give a couple examples and a couple non-examples of this. So let's go ahead and get started by giving a positive, at least in some ways, the simplest possible example. So v of xy is equal to x squared plus y squared is positive definite on all of R2. And you can show this a couple ways. I'm going to draw a picture because this gives you some intuition for what's going on. So this is the x-axis, this is the y-axis, and this axis corresponds to v of xy. So what's going to happen is, well, if you think about this, this is precisely just a parabola in the radius, in the square of the radius r squared plus x squared plus y squared away in terms of your distance away from the v-axis. And so if you draw this out, this is going to look something like this. That's a parabola. Well, let me erase this. I don't think we need that there. This is a parabola. Well, these are the values of the functions, and it's 0 at only the origin point and positive everywhere else. And this is pretty easy to see as well. So if x squared plus y squared is equal to 0, then x equals 0 and y equal to 0, and x squared plus y squared has to be greater than or equal to 0 because you're taking squares. And there are some other functions that aren't positive definite everywhere. So for example, v of xy equal to x squared plus y squared minus y cubed is positive definite in a region near the x-axis. So once you get too far, if you allow y to start getting big, well, then the problem that happens is once y starts getting big, then it can go negative. But in the close enough region of the x-axis, this is positive definite. And with a little bit more work, we could put actual constraints on it, but we're not going to worry about those right now. And let me give a couple examples that aren't positive definite, though. So v of xy is equal to x plus y squared. V of xy is equal to x plus y squared on parentheses. And v of xy is equal to x squared are not positive definite. And to see this, there are a couple ways of doing it. One is you can just give examples, but it'll be helpful to illustrate things if we define something called a level set. So define the level sets of V. Let's put that in blue. The level sets of V are precisely, we're going to use the notation V inverse of K to denote the set of points xy in R squared such that V of xy is equal to K. And note, in order to be positive definite, we have to have V inverse of the level set of 0 to just be the origin. And the level set of any negative number has to be the empty set. And so one easy way to see that these are not positive definite is just to look at the 0 level sets for each of these functions. So v of xy is equal to x plus y squared. Xy. Well, it turns out when you set this equal to 0, that's just x is equal to minus y squared, and that's just going to end up being a parabola here. So this is v inverse of 0. And note that because the level set actually is continuously, touches the origin, this means that no matter how small of a neighborhood you get to around the origin, it still won't be a positive definite because it's 0 in a non-zero point near the origin. And we can do this similarly for, oh, I'm sorry, I copied that down wrong. So v plus x plus y squared. Well, when is this equal to 0? Well, precisely when y is equal to minus x. So this level set goes, so this is the 0 level set for this one. And we had the last one, which was v of xy is equal to x squared. Well, when the level set here is just when y is equal to, or when x is equal to 0. So the entire y-axis. So those are some examples where we can use level sets to see that something isn't positive definite. But what happens when we do actually have a positive definite function? So if we actually do have a positive definite function, then life gets a lot nicer because v of x. And we'll see that this gives us precisely the sort of concentric circles that we talked about in the very first example. So v inverse of k is equal to the set xy such that x squared plus y squared is equal to k. But that is, of course, precisely just the set of points with radius root k. And therefore, the level sets of this, when we draw it out, it's going to look something like, let's see, so there's a level set of 0, which is just the equilibrium. But we also have all these other level sets. So here, that's the level set for v inverse of 1. That's the level set for v inverse of 2. That's the level set for v inverse of, not that, v inverse of 3. So level set where it's equal to 3. And of course, so the key here is that a positive definite function level sets let us construct the regions we wanted. Now, of course, what we have to do is now we have to show that the vector field always points inward along these level sets. And that might seem a little bit difficult, but we do have the vector field already. Let's just x dot, y dot. And so what we can do is we can look at the vector field along the level set, and what we always want to do is point inward. Now, what exactly does that mean? To talk about this, we're going to have to talk about gradients and derivatives. So consider, well, let's consider some path, some solution path, x of t, y of t. Note that because it's an autonomous system, every solution that goes to the same point is equivalent. Let's let this be a solution to our differential system. Well, when we know that the derivative with respect to time of x of v is equal to the partial derivative with respect to x times dx dt plus the partial derivative with respect to y times dy dt. And by doing the substitutions, we know that this is the partial x times f of xy plus partial y times g of xy. So luckily, this has no dependence on time, which makes sense because it's autonomous. And one of the nice things is we can rewrite this as a dot product, which then has a geometric interpretation. So we can rewrite this as the dot product of f of xy, g of xy, dot product with partial x, partial y of v. So this is a dot product. And this here, you'll notice that this is just the gradient of v. And because this is a dot product, we can also rewrite this as the norm of our function, of our f and g, times the norm of the gradient times cosine of theta, where theta is the angle between the fg vector and the gradient. And this is just by using this cosine comes because this is one of the geometric properties of the dot product. Okay, so now the next thing we need to remember is what is the gradient of our function? And it's important that we constructed these things as level sets now. So note, on a level curve, on a level set, the inverse of k for any positive definite v, so the gradient points outward. Why is that? Well, because these level sets are precisely the sets along which going in that direction doesn't change your function. And so you need to go in the orthogonal direction if you want to change the function. And so this is the normal vector. So we have so the gradient of v. Okay, but now what happens when cosine is less than, so if cosine of theta is less than 0, because that was our thing there, well, that is precisely when this arrow points inward, because that means that the angle has to be greater than 90 degrees or less than 100 or less than minus 90 degrees. And we can classify each of these cases. So in the case where, again, so let's say we had the gradient of v, and if the angle was precisely 90 degrees, then that means that cosine of theta is equal to 0. And oh, sorry, that's the wrong color. I'm using orange for this, I think. And in the case, come on. Oh, help. I erased all my drawing. This is the gradient of v. And if your angle is pointing upward. So if it's an acute angle, then we know that cosine of theta is greater than 0. But now, look back up here. You'll notice that the sine of this entire thing, and therefore the sine of this derivative, depends only on that angle. And so this implies that, in this case, we have dv dt is less than 0. Here we have dv dt is equal to 0. And here we have dv dt is greater than 0. So if the derivative is less than 0 for all of these level sets, so for all the level sets, then that means that everything keeps on getting pushed inward. So this is a much stronger condition than what we were doing with the trapping regions in Poincaré and Dixon, where we just had to say that the outside pushed everything inward. Here we're saying everything's pushing stuff inward. And if everything's pushing stuff inward, then eventually trajectories will get squozen down into just the equilibrium, and you can prove global asymptotic stability. On the other hand, if in the middle case, where things are equal to 0, well, then things can't ever escape. They can't ever get away. But they might still, but they might not ever actually reach the equilibrium. This leads us to a theorem, which we've sort of already given the intuition for, and we're not going to prove rigorously, but all the pieces here are going to, are the ideas behind the theorem. So this is the theorem, Leoponov stability theorem. Stability theorem. The full proof is in the textbook if you want to look at that. We're not going to cover the full proof here since it is a little bit technical, and I mean it's a delta epsilon proof. But let's go ahead and state it. So let's let 0, 0 be an equilibrium of the autonomous system. X dot is equal to f of xy, and y dot is equal to g of xy, so our standard setup. And let v be a positive definite function with continuous partial derivatives in a neighborhood U of the origin. Sometimes the neighborhood can be all of R2, sometimes it's much smaller. But this will basically give us what's called a basin of attraction. So so long as you have these Leoponov functions along this in there. We haven't defined the Leoponov function yet. But so long as we have these level sets and certain properties on these functions, then you can prove global asymptotic stability on this neighborhood U because everything gets crushed down into the origin. So let's be a bit more precise about that. So there are several different cases. So if dv dt is less than or equal to 0 for all x, y in U except the origin itself, because obviously at the origin itself that's an equilibrium, and so we're not going to worry too much about that. Len, we know that 0, 0 is stable, and V is a, this is not just locally stable, this is stable for all of U. It's stable, and V is called a Leoponov function. The second case is very similar. Actually, let me copy and paste this so I don't have to rewrite all. Actually, I will need to change things slightly, so let me not copy and paste it. Condition 2, or case 2, if dv dt is strictly less than 0 for all x, y in U except the origin, then 0, 0 is globally, on U at least, asymptotically stable on U. So no matter where you start in U, you're going to end up getting pushed towards it. on U, and V is called a strict Leoponov function. And the third case, well, if dv of xy dt is greater than 0 for all xy in U minus the origin. My pen's not working. When the origin is unstable, because things keep on getting pushed away. So now, there are a couple of issues with this. The biggest issue is there is one major difficulty, which is that finding the correct functions in level sets is hard. It's really easy to construct positive definite functions, but you need to construct a positive definite function such that everything points inward. And that is really quite tricky. And so, in some common cases, though, other people have found Leoponov functions to make it easier to prove stability. So let me give an example. So let's say that we have, this is example 5.28. Let's say we have a Leoponov system. So a predator-prey system that has the following parameters. dx dt is equal to x times a minus y. dy dt is equal to y times minus b plus x. And a and b are both greater than 0. So it turns out there is a positive equilibrium. X bar, y bar is equal to BA, which is stable, but not asymptotically stable. How do we show this? So consider a Leoponov function, b of xy, which is equal to, let me copy this, x minus b times ln of x over b plus y minus a times ln of y over a. Okay, so now I have given you this function, and the first thing you should do is you should check that b of BA is equal to 0, because our equilibrium is BA, not 0, 0, so we have to do all the same logic with respect to the actual equilibrium, or you could translate the system, but often it's easier to think of it as a positive definite function that's just 0 at BA, and b of xy is greater than 0 for xy in the positive reals, and xy not equal to a b. Okay, so we can check that it's positive definite. Let me rewrite this just to make it a little bit clearer. Not equal to 0, greater than 0. Also, you'll note that dv dt is equal to the partial with respect to x and then dx dt, which is just plus dv dy times the partial, that partial derivative times dy dt, which you can multiply this out and take the derivatives. This is 1 minus b over x, since this is the partial derivative with respect to x, times, well, the function up here, x times a minus y. So x times a minus y plus 1 minus a over y times minus b plus x. So this implies that this is equal to x minus b times a minus y plus y minus a x minus b is equal to 0. And therefore, BA is globally stable. But note that we haven't proven that this is asymptotically stable, because it's equal to 0 and not less than 0 in in the positive quadrant, which is what we care about for predator-prey systems, and we don't care about negative numbers of animals. Okay, so that was a lot, but the basic idea behind this lecture is that if you construct successive trapping regions, you can actually show global stability because you can keep on pushing things inward and inward until you squeeze everything down to the equilibrium, in which case it is globally asymptotically stable. Or if you just construct trapping regions successively, even if they don't push things inward, as long as every single trapping region keeps things in place, then you can show that it is globally stable. Okay, and that concludes all of the theory that we're going to be covering in MATC58. The remainder of the videos will be, I think there are, yeah, so there will be a remainder of the videos, I think it will just be one or two more, will be on applying some of these things to specific biological examples. So thank you very much, and I will see you in class.